Okay. So this kind of looks like, let's see, the B side has a thickness of 0.004 and the other two are 0.002. So these thicknesses are obviously exaggerated, but it's something like that. And so I calculated the median area. What was the other one that you? Oh, just the area for the. Okay. Yeah, the total, the actual area. All right. Well, I did it as the outer area minus the inner area, and so I said.
On your solutions, actually, you did thickness times length for the three sides.
Thickness times length for the three sides.
So it was 2 times 0.002 times 0.115.
Oh, okay.
Plus 0.15, 0.004.
Okay, well, that way, all of the limits of those ways of doing it, as the thickness goes to 0, are equal to each other. Okay. And so, but the thicker the thing is, the worse that is as an approximation. I think the way I tend to do it now, when I know it's going to be complicated, is just calculate the outer area, calculate the inner area, and then take the average of the two, and it's a pretty good approximation. Okay. And you know, the thinner it is, I mean, as it gets thinner and thinner, you can just use what's the percent difference between the inner and the outer area? It's small enough that you could just use one of them and forget about it, you know.
Okay, so kind of what you did here is...
Yeah.
Okay.
Okay, so, well, any other homework questions? So now we're going to get into a new topic, which is I guess I kind of give it two different names, macroscopic deformations. Or beam displacements. So far we've done local deformation calculations. Strains are fully local deformations. And they do help determine whether a material is going to break at a point. But sometimes it's also relevant to know what the overall deformation of the body is going to be. For example, like imagine this balcony. And you do your stress and strain analysis and you figure out it's not going to deform enough to worry about anything breaking. But then in practice, the deformation does this, that's not an ideal, balcony.
It's a diving board.
That's how sad it makes you to be on a balcony like that. So even if the strain is low, the strain is small. Well, is it possible that the strain could be small there? Yeah, it totally is possible. Like, if you have a very thin thing like this, with a deformation, this page deformed like this has very low strains. There's no point that has a large strain. Remember, strains, as long as you have a linear relationship between stress and strain corresponds to stress. There's no, that this page isn't anywhere near breaking from me doing this, so it must be a small strain, and it is. But that doesn't mean that the overall deformations are small. Okay. The definition of beam displacement is, if you think of this as the undeformed beam, and then under the load, the beam does this. At each point, at each material point, you can find where that point went under the deformation, and this is a displacement vector. Okay. And at each point, the displacement vector total is equal to the displacement vector due to internal tension plus the displacement vector. This is a new one that we're going to see here, but the displacement vector due to thermal changes plus the displacement vector due to a bending moment. We're not going to have to worry about a separate shear force ones. Those, the displacement due to bending moment and shear force are related through their derivative relationship. So we'll lump that all into one, plus the displacement due to the internal torque. When does this relationship hold? This is superposition again. And this holds for small deformations. Let's say small displacements. So the figure that I drew to kind of exaggerate this would be a terrible case for using this superposition principle. But as long as the displacements are small for everything, we can use this. And in this class, we're always going to be assuming small deformations, small displacements, and so we're going to use superposition. There's one more thing that we're going to use this for. So also, displacement calculations can be used to solve statically indeterminate structures. Okay, so let's think about why that is. So for example, picture a structure that you've done solutions for a bunch of times. So let's say we have an equilateral triangle with a pin on one side and a roller on the other side. And you apply some force to it. Okay, that's not hard to solve. But say that you just want to give this a little bit of extra strength. Like you're pretty sure that this is strong enough, you've done your calculations, but it doesn't hurt to add a little extra strength to it. And so you do a very reasonable thing as you build this. You put in one more member like this. Okay, well, this we can solve with statics. This very reasonable thing that we've done to strengthen this is statically indeterminate. If you try to solve it with statics, you'll end up with more variables than equations. So, but I mean, it's a very reasonable thing to do. You've done similar enough things to this in your life that the world isn't gonna, it's not gonna cause a black hole or something to do that, So what is it? Like you can't solve this system, but it's a perfectly well-behaved system. Like how would you go about solving that? And the answer is you would use beam displacements to come up with the extra equations you need. What you would say is you would calculate the deformation of this diagonal member at that point. Okay? You'd calculate where that point went under the load. You'd calculate the deformation of, the displacement of that corresponding point on this member. And you'd say that that pin makes them be in the exact same place. Okay? And that gives you another equation that using the deformation, like the way that these materials deform, it gives you another equation that lets you solve this, And if you think about, think about how this would behave with different materials here, and it makes sense that you'd have to take deformation into account. Like say that, so with statics, you can solve this. You don't have to know anything about the materials. But over here, well, what if all of these three were made out of silly putty and this was made out of steel? This structure would deform one way. Now think of this is all, or these two are steel and these two are silly putty or whatever. It would deform a totally different way. Okay, and so it makes sense that you have to consider how the materials deform in order to figure out a solution. So here's a roadmap for what we're going to do, because this is all going to take a little while, but overall the kind of game plan is simple. We're going to start with tension and compression. And I'm lumping in with this thermal expansion. And we're going to start out by calculating displacements, just come up with how to do the calculation of the displacement of a point under deformation. And then once we've done that, we're going to apply it to statically indeterminate structures. Then we're going to do bending moments. And we're first going to deal with beam deflection, which is the kind of displacement that you get for bending. And then after that, we're going to apply this to statically indeterminate structures. And then the last one is torques. And again, we're going to start out by calculating the displacements, which is angle of twist. And then we're going to apply that to statically indeterminate structures. And what did I say about shear force? Like, that's sort of a notable omission here from this list. Why isn't shear force on this list? Remember that, so we've always taken advantage, just as kind of a check for the most part, of the derivative relationship between the bending moment function and the shear force function, okay? Because of that relationship, the effects of both of those two fall under this bending moments displacement, okay? Everyone with me on that? Okay, so I'm going to start out with tension, compression, and thermal expansion. Now really to calculate okay, so strain is like a local deformation. And so if you wanted to get a total displacement deformation of an entire beam, it kind of makes sense intuitively that the way you would do that is just integrating up those strains that come from tension or compression. And so that's the way it works. Let me give you the formulas first, and then I'll just sort of explain where it comes from quickly. So the integral definition and this is for continuous changes in the shape or the load of a material, is that the displacement of the end of a beam is equal to the integral over the length of T dx over the Young's modulus times the cross-sectional area. If the shape and the load are piecewise constant, then you can use a sum formula where the displacement is the sum over all of the pieces that you can break it up into of t for that piece times the length of that piece divided by e for that piece times a for that piece. And you can see that that totally matches the definition of the integral definition, as you would expect. Where do these come from? All we're doing is integrating the strains over the length of the beam. So if you start with the definition that, so we know that sigma xx is t over the cross-sectional area. And we know that the xx normal strain is 1 over E times that xx stress. So we can plug that in as T over EA. You can see this is already starting to take that shape. And we can also think of the definition of this strain as, so this is the change in length over the length, right? That's just the definition of that normal strain. And we can think of this as the change in the displacement, the change in length with respect to the x location. So we're going to set these two equal, and you get that du dx is equal to t over EA. And so now just use separation of variables to integrate this, and you get du is equal to t over EA dx. You can integrate it, and so that's it. Just coming up with definitions of the strain and then integrating over x. We're not going to use the integral formula much. We're going to use that piecewise constant formula more often. So let's do an example with that. So let's say we have a post connected to the ground, and let's say we have 3,000 newtons that way, and at the midpoint we have 5,000 newtons this way. And we want to know what's the displacement. And a lot of times you'll see this written as delta, the change in length at the top of the pole. Okay, well, when we were calculating stresses in beams due to internal loads, the first step was always calculating the internal loads, and it's the same thing here. It's not these external loads that matter, it's the internal loads on the different sections. Okay, so I'm gonna sort of turn this sideways and start out by calculating the external loads. I'll call this R. We have 5,000 this way, 3,000 this way. Everyone with me on this? So my free body diagram is like looking at it this way. Wow, look at this cool pole I found. That's so awesome. That's you.
Do they have giant observers like when you're doing, material studies for actual materials?
Yes.
Okay.
Yes, they do.
Good to know.
And yeah, they're very snitchy, so you don't want to take your lunch break too early or anything. Okay, so Newton's second law then, I'll just do it along the x-axis. Says positive R minus 5,000 plus 3,000 is equal to 0. So R is equal to 2,000. And now I'll do my cuts. I didn't give a length for any of this. Let's say we have half a meter for each of these. And I need to give some dimensions here too. Let's say that the Young's modulus is 100 times 10 to the 9 pascals. And let's say that the cross-sectional area is 0.01 meters squared. Okay, so for our first cut is for 0 to 0.5. We have a 2,000 Newton force this way. We haven't gotten to the 5,000 yet, so the only other thing we have is an internal load. And so Newton's second law in the x direction says 2,000 plus t is equal to 0. So t is equal to negative 2,000. And then for cut 2, for x's between 0.5 and 1, we have the 2,000. We have the 5,000 going this way. And the internal tension. And Newton's second law in the x direction says 2,000 minus 5,000 plus t is equal to 0, so t is equal to 3,000. Now we can use the sum formula for the displacement. So the elongation is equal to the internal tension for the first piece, which was negative 2,000. You can trust these signs again, times the length of the piece where this internal load applies. That's over the interval from 0 to 0.5. Divided by E, 100 times 10 to the 9, times the cross-sectional area. And then we have the same thing for the second part. On the second part, our internal load is 3,000, positive 3,000. The length of the second part is 0.5. On the bottom, we have 100 times 10 to the 9 times 0.01. And what we get here is 5.0 times 10 to the minus 7 meters. What does the sign tell us? Positive means elongation and negative means contraction. And that sign convention comes from the fact that a positive value of T is tension and a negative value is compression. Any questions about that? Let's do another example. I will do this one with the integral definition. So for this one, let's say we have a material that looks sort of like this from a side view. And let's say we have a 20,000 Newton force on this side and a 20,000 Newton force on this side. We'll say that the whole thing has a length of 0.5 meter. And let's say that the material is steel, so the Young's modulus is 200 times 10 to the 9 pascals. And the cross sections, we're going to say on this side go from, these are all squares, and they go from having side lengths of 1 centimeter to side lengths of 6 centimeters. And again, we want to calculate the elongation. Okay, well, we know that we're going to use this equation that says the elongation is the integral of t dx over EA over the whole length. So this is for this is for x from 0 to 0.5. And we would, okay, so we know that the side length goes like this. So for x, let's calculate the side length. It starts out at 0.01 meters and ends at 0.06 meters. Okay. And so we want an equation for that line in terms of x. We're trying to put everything in terms of x so we can integrate over x. So how would we get an equation here? Well, the slope, you know, I'm going to do this as y equals mx plus b. The slope is the rise, which is 0.05, over the run, which is 0.5. So that's 0.1. And so the equation is y is equal to 0.1x plus the y-intercept is 0.01. And so the area then is, at any given x value, the area is the length squared. Right, that's a square cross section. So this is equal to, I'm going to write this as, I'll pull the 0.1 out and make this x plus 0.1. And so this is equal to 0.1 squared, 0.01 times x plus 0.1 times x plus 0.1. You with me on that? Well, now we can start plugging this stuff in. So our delta is the integral from 0 to 0.5 of, well, I didn't do the cut, but let me just do the cut. So cut 1 is valid over the whole length. You have 20,000 over here, and the internal load T here. So Newton's second law in the x direction says negative 20,000 plus T is equal to 0. So T is equal to 20,000. Freeze. So now I can plug this in. Delta is equal to the integral from 0 to 0.5 of 20,000 dx divided by, I pulled out that 0.01, times e, which is 200 times 10 to the 9, times x plus 0.1 times x plus 0.1 I'll simplify all the numbers. So what do we have? 20,000 is 200 times 10 to the second. So that's minus 7 minus 9. So we have 1 times 10 to the minus 9 times the integral from 0 to 0.5 of dx over x plus 0.1 times x plus 0.1. Anyone have an idea how to do that integral?
Multiply out the factor and then rewrite it as a multiplication with negative exponents. Probably the easiest way.
Write it out as a polynomial?
Yeah, with negative exponents.
I think the fact that having it factored like this, to me, says what we want to do is say u is equal to x plus 0.1. You know?
I was never good at that.
So du dx is equal to 1. So dx then is equal to du. And then we can rewrite this 1 times 10 to the minus 9 times the integral. So now we can replace the x's with u's as long as we also replace the bounds of integration with u. So plug in 0 for x, and you get a u that's equal to 0.1. Plug in 0.5 for x, and you get a u that's equal to 0.6. And now we have du over u squared, or in other words, I can write this as u to the minus 2 du. And so that's 1 times 10 to the minus 9 times negative 1 over u. And we're evaluating this from 0.1 to 0.6. And so we have 1 times 10 to the minus 9 times 10 minus whatever 1 over 0.6 is. And we get an answer of 8.3 repeating times 10 to the minus 9, and this is meters. Is this Elongating or contracting? Yep. Positive, so elongation. Any questions about that?
Yeah, to the negative now, right?
That's what I got, yep.
Okay.
So that's pretty tiny. So that won't have any consequences on any design decisions you would make, but that's how you do the calculation. All right, that's it for today. And we'll get into, I think the next thing we're going to do is get into oh, wait. This will be quick to fix, but so I multiplied all this by the 0.01 instead of dividing by the 0.01. So this should go from, this should actually be 1 times 10 to the minus 5, which has a pretty significant effect on all this. So this is minus 5. This is minus 5. And this is minus 5. Okay, well, I just made a math error in there.
And then that middle 1 e to the minus 9th is the same?
Nope, that's also.
Okay. So 10,000 times bigger.
Yeah, that's a big difference. Try not to make mistakes in your engineering career that cause a factor of 10,000 error. That's how you get 35W bridge collapses and stuff.
That'll be fine.
We're watching the series community.
What? No.
Plot point is at the end, they let a really bad engineering kid make a bridge. And it just falls apart.